Okay, so chapter 9, problem 39. I will give you a heads up. This is a little bit of a long problem, but I'm going to try. I've prepared a lot of pages for this, and so hopefully I'll be able to go through them quickly so it doesn't take too much time. But there's a lot to talk about, so let's just try to get through everything in a reasonable time. So 4 bricks are to be stacked at the edge of a table, each brick overhanging the one below it, so that the top brick extends as far as possible beyond the edge of the table. Part A. To achieve this, show that successive bricks must extend no more than, starting at the top, a half, a fourth, a sixth, and an eighth of their length beyond the one below. And this is in the figure 9-75A. Part B asks, is the top brick completely beyond the base? Part C says, determine a general formula for the maximum total distance spanned by n bricks if they are to remain stable. And finally, part D, a builder wants to construct a corbeled arch based on the principle of stability discussed in A and C above. And I suppose this should be, well, there hasn't been a question yet. So yeah, here's the question. What minimum number of bricks, each 0.30 meters long and uniform, is needed if the arch is to span 1.0 meters? Okay. So one thing we haven't talked about at all in this chapter is the center of mass. And so I just want to introduce that concept real quick. It's going to be very useful for the first part of this problem. But yeah, this is the center of mass, just a very simple, this is right in Goldstein mechanics textbook. You can find this in most other textbooks. It just might be under a different name than R. I just like to use R generally. This is how I learned about position when you're talking about center of masses, but you can use anything here. It can be X1. You can really call this X1 if you want, or XI or something like that. So it's just my preferred nomenclature to use RCOM. It just means the center of mass of the position, which is it's the position center of mass. So what does this mean? What is all this for? So if let's say I had on some coordinate system here a couple different points, a couple different mass points, M1, M2, M3, they all have different masses, they're all different distances away, and I wanted to calculate their center of mass, then really all I would do, so hopefully you remember that, I need the space real quick. All I would want to do then is with 3 masses, I would say, okay, M1 is at X1, and M1 is at an X1 position, M2 is at an X2 position, and M3 is at an X3 position. And then I would divide it by the total mass, which here would be M1 plus M2 plus M3, right? So you can see each individual position has a mass associated with it, and you basically want to sum up all the possible combinations, or not combinations, but all the possible masses and distances that are attached to each other, and then you want to divide by the total mass. And this will end up giving you a position again, right? Because we're dividing a mass by a mass. So m sub I is the ith mass, x sub I is the ith distance, and so this just makes it general for however many bricks we want to include. If it's 2 bricks, 0 bricks, 1 brick, infinite bricks, whichever, or 7,000 bricks. How about that? So just to get right into part A, the max distance the first brick can go is determined by the center of mass of the system. So this is a very important concept to learn. Hopefully that helps you in the future, what I just said before, but we can just do the calculation very quickly, very easily here. So for 2 bricks, we have the center of mass of, essentially when you're doing 2 bricks, you're really working for the center of mass of the one, because we already know, you can see from the picture in the book at least, that when you put the one brick on top of the other, then we'll shift it a little bit so that the center of the first brick is at the edge of the bottom, the one under it. Then it turns out that the center of mass is just halfway in between So L over 2. But let's go through the calculation just to see. So we have one mass at 0, who has not moved from its original position. Essentially, like there's nothing really over here. Plus, well, yeah, we really should just say that we only have this part, right? We have one mass sitting on top of another, well, one mass sitting on top of another, the 2 bricks, and the center of mass of the first one is at L over 2, or the position it's at is at L over 2. And we also want to divide by the total mass, but there's only one brick to consider. Now I know it says so for 2 bricks, right? This is, let me maybe draw a picture, it will help. So if you have a brick like this, and a brick like this as well, just what they mean. There's putting a brick on top of another brick like this. So in some sense, it's a center of mass for 2 bricks, but really we're only talking about the 1 brick here. So this is going to be RCOM1. And then as we go farther and farther down, the distances are going to change. So for 3 bricks, we want to say, like I said before, it's always kind of like you're dealing with 1 less brick than what you're actually saying. So for 3 bricks, we're really doing 2, right? So RCOM2 says m times 0 plus m times L over 2 again, same thing. But now the total mass is going to be 2, because although the position is the same of that top brick, there's been more bricks added. So now we're dealing with those 2, and then when you divide this, you get L over 4. And so this goes on, just so on and so forth, the same way. You just, essentially, you're adding more each time to the bottom, adding 1 more mass to the bottom, and just adding 1 more mass to the top as well, actually. And so eventually these cancel out and they'll give you different terms. So you'll get L over 3 if you calculate the center of mass for a set of 4 bricks, but for the 3rd brick, it's going to be the center of mass of that one is going to be L3rd. But if you go back to the first brick, it's actually a 6th from there. So this is where we start to see that relation that the question is looking for. So we start with L half, and we go to L fourths, and then next should be L sixth, right? So this is all referencing from the first brick, because when we're calculating the center of mass of each of them, we're really doing the ones before, like the few bricks before. Well, actually, not the last brick. Sorry, not the before bricks. So we're not including the first brick that we put that's on top there, but that's what we really want to answer the question with when the question says, to achieve this, show that successive bricks must extend no more than a half, a fourth, a sixth, and an eighth of their length. So it's a sixth of the first brick's length, but a third of its own length, so on and so forth. And so this is where we get that part from. So part B, well, this one's very simple. After we've done all of our calculations, we just want to add all the distances that we calculated from part A. So it's just L half plus L fourth plus L third plus L, sorry, no, that's wrong. L half plus L fourth plus L sixth plus L eighth. And so if you worked with some fractions, do a little bit of work with the fractions and get them all with the same denominator, you'll find that they add up to 25 over 24L, which is greater than L. So it turns out that the first brick is going to be completely off the edge of the table. So it's going to be sitting kind of like, if we have bricks like this, it is definitely sitting somewhere in the middle like that. Far away from it is off the edge of the table. And then now we want to find the general formula. So the answer to the question, is the top brick completely beyond the base, is yes. It is beyond the base. Okay, part C, the general formula, as we had just like we used here, our comms from 1 to 4. we're basically just going to add these, and then if you notice a pattern, it turns out that if you multiply by 1 at the bottom, there's always a 2 multiplied by some kind of incrementing factor. So for the first one, for example, you have L over 2 times 1, and then it could be L over 2 times 2, and then L over 2 times 3, and so on and so forth. And so once you notice this pattern, you can say that the sum goes on until L over 2n, and so then we can write our relation very easily. Our general formula for n bricks is going to be the sum from I to n of L over 2i, where it should be obvious, but just to be clear, I cannot be 0, right? Because if you divide by 0, go to infinity, right? So don't divide by 0. So it should be, we can write here, I equals 1, right? Right, so now part D. So we want to find out what's the number of bricks it takes to span 1 meter. So the arch is to span a meter, so one side will span half. I mean, so this is fair to say, right? So if we have a full meter here, the arch is going to span half of this meter. So we're expecting the bricks halfway, half from here, half from there, right? So basically what we have to solve is, since we're given this, we were given a general length before, right? It was always just L. We were never given a number, but now the problem has told us what minimum number of bricks, each being 0.3 meters long and uniform, is needed if the arch is to span a meter. So given this length, L equals 0.30 newtons, we can just plug that right into our relation that we found, our not relation, our sum. That's what I meant to say. Yeah, the sum that we calculated, the pattern that we followed, plugging in L there, and then really taking I. We want to find n such that the left term here. So that's let me use a different color. We want to find n such that this term here is going to be greater than or equal to 0.5. And so the evaluation of this expression shows that at about n equals 15, the span begins to approach. Well, the span approaches 0.5. So I think at 15, it should be about like 0.476 or something like that. So really, you need 16 to span it. So let's just go to the last page. So yeah, at 16 bricks, 0.507 meters is spanned. Now we have to also think about a few extra bricks. So we have 2 base bricks that were not counted in, and then there's going to be one on top as well. There's going to be 1 brick above the 2 bricks that meet. And so this essentially means that we're going to have 16 plus 16 plus 3. And so we have 35 bricks in total that will span the arch.